So today we'll look at doubly linked list. In the previous lecture we had a look at singly linked list, and singly linked list would typically look like this. So in singly linked list there were next pointers, and the next pointers allowed us to move or hop from one node to the other node to the next node, which could be distinctly placed in the memory. Like the memory could have these individual spots, and these individual spots are allocated and assigned the relevant data, and then through the help of these pointers that were part of this data structure node, we are able to basically link all of these and hop. Now if we look at this becomes evident that we can only traverse in one direction, right? So that means if I'm traversing the linked list and I begin from head and I reach to the kth node, now it could be so that from the head till k, all the nodes that I have traversed so far need some update. Consider that I have a request wherein I have a linked list, and there is a request to increment nodes up to 30th position if 31st element is 10 or less, right? So we start traversing, we reach, so at some point of time we reach the 31st element and we find that to be 9. Now there is no way that we can basically go back and update these 30 odd nodes. So we have to basically start again from here and traverse to the 30th node again, and one by one we have to increment each node. So this presents a very inherent limitation in the singly linked list. There is another example, simple example we can take, is that we are traversing and then suddenly this node has to be deleted because of a decision point. So there's a decision point, like we could say update the linked list such that all elements less than a value k have to be deleted. So in that case, while we are traversing the linked list, we can find this, and a particular set of nodes in our way, and we need to keep deleting them. Now the problem is when we are traversing, we are here. Now we have no means to get here. So the linked list does not provide any mechanism to go back to the previous node, right? So when I decide to delete this, then the previous has to be connected to this node. So at that point of time, we have to do additional bookkeeping for the previous node. So to do away with such limitations, an update to the singly linked list was thought of, and the update basically means that the data is connected bidirectionally. So what this means is that we have a next node already and we add a previous node to this. Now an obvious downside to this is memory usage is increased because we now have to store 2 pointers. So as our linked list grows, we have to have 16 bytes per node, right? Because in 64-bit systems you have 8 byte pointers. So if you have 2k elements, that means 2 raised to power 10 into 2 into 2 raised to power 3. So much amount of bytes will be used extra or additionally in the memory. Now this also means that whenever we are updating the linked list, so we have to ensure that both sides are updated. That is, if we are deleting any node, right? So if we are deleting this node, then the node has to be connected to the next node. So this has to point to the next, and the previous of the next has to point to the data node here. So that means performance of all operations like insertion, deletion is degraded because we have additional work there, right? Now let's look at the node, how this will look like. So I have a struct, and I would say double linked list node. Now in the single linked list we had a data type, data element, right? So this is the primary data storage, right? The main purpose of having this data node. And then you have DLL node pointers. So one would be previous and one would be next. So both of these, mind you, are pointers. So they are not actual nodes, they are pointers to nodes. Now let's look at how the double linked list would start to form. So the concept is same. I have a head, right? So the head initially is pointing to null because the double linked list is not yet formed. To form the double linked list, first of all, is I have to populate the head. So first, I will take a node, DLL node, right? And I will do a new DLL node, and then the value with which I want to update this data element here, right? So when I have this, so consider this was the node n. Now head has to start pointing to n. So once the head is formed, so now I have a node, right? And this node has two pointers, both of which are initialized to null pointer by default, right? So they are both pointing to null, and I have my value here, right? And now my head is pointing to this node, right? Based on how the compiler puts your data structure in memory, you could imagine something like this, that you have a value here, and then you have a previous and a next pointer. So this is 8-byte address, this is 8-byte address, and this is size of your data element. So how much ever size, because this is custom value, so you can allocate how much of size is there. Now in memory you will have one node like this, and then someplace else you will have a similar node like this, right? You have a similar node like this, and then someplace else you will have a similar node like this, and then someplace else you will have a similar node like this, right? So here some place the next will be null, right? So previous here would be null, right? Next here would point to this value, right? So previous here will point to this value, and next here will point to this value. So previous here will point to this value, next here will point to this value, previous here will point to this value, and next is null, right? So this is a somewhat symbolic memory view of your doubly linked data, doubly linked linked list basically. So the operations are similar. We have insert, we have delete, we have count, we have display, we have delete all, and so on. So the advantage here is that we get automated bookkeeping for the older traversed nodes. So the bookkeeping is not that we are actually storing, no. So we have already stored this in memory, and it's not that we are storing things on stack in temporary variables. So that is not the case here. So to do away with having to save all this prior node information on stack in temporary variables, we have basically consumed additional blocks of memories. And let us see this in action. So let's create a doubly linked list, right? So this is head, right? And then this is null. This is the previous one, and then this is null, and this is data element D0. Now this is my doubly linked list, right? Now my first operation is insert. Insert can again happen at beginning, at middle, at end. So in this case, let's look at the fact that I have a new data element called D1, right? Now I have to make this a part of this linked list such that D1 gets added prior to D0. So the process remains similar. First, I will create a DLL node that has D1 value, that carries D1 value, right? So now I have D1, right? D1, and I have these two nodes which are pointing to null, right? And then I have D0, again, both of these pointing to null. So the way to insert at begin is that I have my head here, right? The head is here. So first, I have to basically connect D1.next to D0, right? Because the prior element of D1 has to be null, so this is fine. So let's look at the final form, right? So we have to connect these two, and then this is fine to be connected to null, right? So now the connection here, if it were a singly linked list, would be just this. But because it is doubly linked list, so that means D0.previous also has to be updated. So D0.previous here will need to be updated to D1. So as you can see, this is a two-way connection. So the n+1 node should be updated with n information, and n information should be updated with n+1 information. So it works both ways, and that's why it allows us to go both ways, and that's why we call it a doubly linked list, right? Now, so once we have this connection established, so we have established this connection by this, and then we will establish this connection by this, right? So once we have established both of this, so our linked list will look like D1 and D0. This goes to null, and this comes from null. Right. So now we look at inserting the middle. So before we do that, let's insert at end, right? So we have D1, and then we have D0, and let's now add D2 to this. So the process is simple. You create a node D2, and you have two pointers with it, right? So the D0's next pointer now needs to point to D2, and D2's previous pointer now needs to point to D0, and then this can point to null. So now we have this, and now somebody asks us to put D3 in the middle, right? So how do we put D3 between D0 and D2? So it's again very simple. So you have a linked list which is doubly linked. So you have connections D0, D1, D0, D2, and there is a new node D3, right? And I have a pointer here and a pointer here, and I have a pointer here, and I have a pointer here, right? So what we need to do here is we have to break these two, and this has to point to this guy, this has to point to this guy has to point to this guy, and this guy has to point to this guy, right? So there are 4 connections that need to be established. So between D0 next, D2 previous. So these were the original connections between D0 and D2. So D0 next has to connect to D3, and D2 previous has to connect to D3, and then there are 3 new connections, D3 next and D3 previous. So D3 next has to connect to D2, and D3 previous has to connect to D0, right? So you understand. So these 2 are new connections, and these 2 are relinks. So earlier these both were connected, but now we have to break this apart and connect them this way, right? And to establish this link, we need to do this thing here. So we need to connect D3 to D2 and D3 to Z0 such that D0 and D2 are connected now through D3 and not directly, right? So we have looked at insertions at beginning, insertion at middle, and insertion at end. So let's understand the time complexity here. Now in terms of time complexity, we do not gain much. So it's still of the order of n, but yes, the fact is that if I were to say reach very deep in the linked list, and then say I have to go a few elements back, like 5 elements back, right? Or 15 elements back in a 200 linked list node chain. So going back 15 and traversing, going back 15 from say I was at 150th node, now I have to go back to the 135th node, right? Now this would mean going back 15 nodes, but if it were singly linked list, it would mean traversing 135 nodes. So even though the order of n value is true, but backward traversals are much more efficient here. So if there are backward traversals which are close by, we can save a lot of time instead of having to traverse the list from the beginning. But obviously it comes at a cost, because now the space complexity increases, right? So it becomes twofold. So let's now look at the next operation, that is delete. So if we have a doubly linked list, which we can represent like this, so we remember that when we had to in singly linked list, we had to connect this to the next node after we used to delete this. So for that, whenever we delete, we have already discussed this, so we have to see that before deletion we move the data that is important, like in this case the address for next element is important, right? So because we have to connect this thing to this node, right? So this becomes important, the node part of this, right? So So we would move this into a temporary variable, right? And then we would go about doing the deletion, and then we would use this temporary variable to make the update on this predecessor to point to the successor, right? Now in doubly linked list, what we have is you have a node that needs to be deleted, and it is connected in two ways. So you have to break the shackles between this and between this, as well as between this and between this. And what you have to do is point this to this successor and point the successor's previous on the predecessor and the next to the successor. So next will get the successor and previous will get the predecessor. So the process is similar. So first is to take the data of importance. When I say data, I mean whatever is the information about the data structure, right? So take the information about data structure that is important from the node that is to be deleted. So it is like a two-way process. First we prep and update, and then we delete. So this is the prep step, right? And then we do the next step, that is update the previous next as deleted next, right? And update deleted next previous as deleted previous. Or I could say deleted previous next as deleted next, and deleted next previous as deleted previous. And third would be delete the actual node. So in here, this is the information point that is important. So we need both of these things. So what is the next? What is the previous? And then we can basically access these fields because we have information about this. Then we can make the accesses in these fields and then update them. And then we go about doing the actual freeing of memory, right? As we can see, the time complexity for the operation again remains O of n because we have a traversal, right? So we can't avoid the traversals in linked lists. So we can make them more optimal for the average case, but it will still remain to be of order n. Now delete, as we know, has unique cases. We can delete head, we can delete something intermediary, or what we call a node in the middle, or we can delete the end or the tail node, or head or the front node here. So let's look at the three cases that we have. So we have the head in all cases pointing to this. Right. Now, if this were the head node and this was to be deleted, and in this case an intermediary node here is what needs to be deleted, and this here is the one that needs to be deleted, right? So here the process is as I described earlier, right? So what we will do is we will snap this information, right? So here let's have a temporary variable temp, and this is equal to a. So we basically have all the metadata from A going into a variable temp. And now the second stage that we have is that we update the head to be B, right? And this is basically what? B is temp dot next, right? And then we say temp dot next previous is equal to temp dot previous, right? So there is no need for us to update null in this case, because we can't do a null dot next is temp next, right? So this is not something which we will do. So we just have to update the link to the previous on B, and then we free the A node, right? So the new head will then point to this, and this points to null because temp dot previous is null, right? And that's about it. So now let's look at the other one here. So we have node A, node B, and node C here, and let's see. So if we were to delete B, we were to first have a temp equal to B, right? So once we have copied the contents of B to temp, then we are free. So A dot next. So how do we get to A dot next? B dot previous dot next is equal to B dot next, right? That's how we update this. So A dot next will be updated. We update A dot next as B dot previous dot next is B dot next, and then B dot next dot previous is B dot previous. So first we connected B dot previous dot next. That means B dot previous means this thing pointing to A, and then its next B dot previous is this, and then its next is pointing to B dot next. So we've connected to this, right? And then on the other side we do B dot next. So we have a previous pointer here, which then connects to B dot previous, which is A, and then we go about freeing B. Third one is we have A, B, and C is null. So temp is equal to B. Then we do the updates. So A, that is B dot previous dot next, is equal to B dot next. That is null, right? And we do not need to update null dot previous here. So this we can do away with, and thus we go about and freeing B, right? So this is what we do in the three cases of deleting the nodes. So with this, we complete the basic operations of insertion and deletion. Count is very simple. You can start with the head and continue till tail and keep incrementing a variable. Similarly for display, instead of incrementing, you could put it on the stdc out and delete all. Yeah, we can look at delete all. So delete all is again similar to what we have seen earlier. So if we have a linked list singly, so what we used to do was we used to hop like this from head till the time that we reached the state where this was null terminated, and each time we would bookkeep the next pointer and then go about deleting the current pointer. So we will keep a previous pointer and we will do the current pointer deletion. Sorry, not the previous pointer, the next pointer. So we would bookkeep the next pointer here and then go about deleting the next pointer, current pointer. So here, even though we have additional links, it does not change much. So we can continue to follow the same process of iterating in forward direction and then deleting this. So this helps us complete the basic operations of double linked lists as well. And next time you would see something like a circular linked list.